Who is the electronics team? We've got Sam Parker, our microcontroller expert, Oliver Merton, the drivetrain designer, Dylan Filkins, designing the drivetrain also, Jonathan Brawl, the new guy, David Brennan, designing our battery pack and enclosure, and me, Braden Hampson, the subsystem lead. And as of right now, you. We're glad to have you on the team. What do? We turn these into this. So, how do we do it? Well, I'm glad you didn't ask, because this is a video, and I can't hear you. Altium is our PCB-designed program. It's the industry standard in the electrical engineering world. This is an extremely powerful tool, and if you don't use the program at least once in your career, come find me, and I will eat a hat. I won't go into detail about how much I love this program. You'll know soon enough. Just watch this. You can search the largest electronics distributors such as DigiKey and Mouser from right inside the program. You can search up your part, right-click, hit place, and it's added to your program. No more needing to go looking around online for that elusive footprint anymore. In the dark days, we used to use PIC MCUs. We suffered through poor documentation, awkward programming, and a 10 gigabyte development environment, until one day we were saved by the STM32. They're easier to program, they have an Eclipse-based IDE, and they have their programmer right on the board. They're pretty alright. I wish there was a program where we could take our 2D paper sketches and make them 3D. Oh, nice. Next they'll tell me I can take data from real-world cell testing, put it into a simulation which models the cooling of our battery pack, and to tell us if it'll overheat. Damn, SolidWorks is cool. Remember these? These are 18650 lithium cells. We take 12 in parallel and 12 in series. You get a 12S 12P pack with 144 cells. We wrap all that in polycarbonate and make 6 of them, all connected in series for 72S 12P pack. We wrap that all in delicious aluminum. You got yourself an accumulator going. The accumulator lives just behind the driver, and as I'm sure you can imagine, the driver would appreciate it if the thing didn't explode. So as I alluded to earlier, cooling is very important. We've done extensive CFD analysis of the pack. Notice how all the clusters of cells are arranged the same. Also notice how there's a hotspot at the rear, and a lot of air escaping at the top and the bottom. We flipped the arrangement of every other cluster to create a wavy pattern. We also eliminated the air pass by in the bottom of the pack, which eliminated the hotspots and gave us a much better pack. Let's take our 12 cells in parallel. Suppose one of the batteries short circuits. What would happen? All of the cells would dump their energy into it. For this simulation, let's replace one of the batteries with an approximation of a shorted cell, a 100 micro-ohm resistor. You can see that a lot of current is being put through the one bad cell. If we didn't do anything about this, well... So let's do something about it. We take a sheet of nickel and cut this special shape out of it. This is an integrated fuse. The idea is that when too much current is put through the cell, the fuse will blow. This is then spot welded to the top of the cell, and it's also how we get the energy out of the cells. We call this the fuse bar. So, How do we know if a fuse will blow at the right time? We need to test it at 300 amps. How do we make 300 amps? That's a really good question, but I still can't hear you. We decided the best way to get 300 amps was just Ohm's law. We needed a way to control the amount of current in, so we took a bunch of 0.56 ohm resistors across 7 boards and hooked them to MOSFETs. We have 70 resistors in total. All we have to do is turn on a MOSFET, and that resistor is now in parallel with the other resistors. Each parallel resistor we add reduces the total resistance and increases the current available. See, Ohm's law. The EVCU is the electric vehicle control unit. It's the brain of the car. It will control everything on the car that isn't the safety shutdown circuit. Its primary purpose is to send the driver's throttle input to the motor controller, manage the power output of the car, and send data to the driver's display. This is the major CS project on the car. The safety shutdown circuit is where the majority of the EE talent will go. This system consists of many parts on many boards, some with high and low voltage. Every single part is critical to the car functioning safely. We have the groundwork for most of these boards, and we know what the circuit should look like, and we know how they're going to function. However, they need to be gone over to be sure that they're rules compliant, and they all need to be put on a PCB. Finally, because it's the last place our electrons go, is the drivetrain. This is where electrical engineering meets mechanical engineering. It's where our motor sends power to the wheels. We use an MRAX 208 permanent magnet motor, connected with a chain drive to our differential. For this project, we are coordinating with our chassis and suspension teams. For our car, our differential carrier is also where our suspension mounts, which isn't shown in this picture. If you are a mechanical engineer with an interest in the electrical side of things, I highly recommend. You may be wondering, how do I get assigned with a task? What does building something actually look like? Here's everyone's favorite, very confusing diagram, a flowchart. First off, it starts with an understanding of what you want to do on the team. Not what you're good at, but what you want to do. I'll assess what the team needs and think about what I think you'd enjoy on the team, and then tell you about a project. You can either say, sure thing, or nah man. Of course, that's not to say you can't come to me with a new widget that you think would really benefit the car. From there, we check the rules. Which ones apply? What restrictions are there? We check what is already known. Has anyone worked on this in the past? What did they already find out? And what did they struggle with? What should the thing do? What are the goals and limitations? This is also where you should ask, how am I going to build it? And what other systems does it interact with? On to the fun part, design. Here you design and document. You also collaborate with anyone you think can help. During this whole process, you should update the team on your progress. That way there are no surprises when you go to implement the design. Once the design cycle is done, we actually build the thing. With any luck, you'll get to hold the part you built, which is always a good feeling. Until we go to test it, and then the nerves hit. But let's say hooray, it worked. At that point, you'll start over, be given another task. Oh, and did I mention the most important thing?